Hello, I'm John Duggan, and this is the TheoryStation. This program is the Principles of Math program. We are on the series Basic Ideas. This is the fourth installment of the series. Previously, I talked about my schematic for mathematical modeling, and a little bit about logic, a little bit about number systems, and now I just want to spend a few minutes talking about equations. Again, very simple stuff. I'm not going to do anything difficult here that you probably haven't seen already. So, but anyway, it'll just get us thinking about this stuff and getting us warmed up. So I'm just going to start with a super simple equation. 3x plus 5 is equal to minus 2x plus 15. So I think we all know how to solve this. It's super easy. But let me just give an analogy that I think is useful for thinking about solving equations. And that is the analogy of a scale. So this equation I think of as telling us that there is a perfect balance. My scale is not going to be very fancy here. It's more like a teeter-totter or something, but it's perfectly in balance. And on one side of that is 3x plus 5, and on the other side is minus 2x plus 15. So these quantities are exactly the same. And we just don't know what x is, so it's like a puzzle or a mystery that we have to solve. So what we're going to do then is, we want to keep the scale in perfect balance, but do the same thing to each side repeatedly, so that we're always keeping that balance, so that we end up with just x by itself on one side, and then on the other side is some number. Since we've maintained that perfect balance the whole way, well, now we know what x is. That number is the solution. So what are we going to do? In this case, this is super easy. So I would subtract 5 from each side. And then if I simplify the left-hand side, that's just 3x. The right-hand side is minus 2x plus 10. And in terms of the scale, I have 3x on one side now, minus 2x plus 10 on the other. Let me add 2x to each side. I don't know what x is, but whatever it is, I'm just adding 2 times that to each side. So it's the same thing I'm adding to each side that maintains the perfect balance. And that gives me 5x on one side. And then the 2x and minus 2x cancel, so I get 10 on the other. So that's 5x and 10. Our scale is perfectly balanced. And then I divide each side by 5. The 5's cancel out, and I get x by itself on one side. That equals 2. And that is the mystery number. We've solved the equation. Okay. So that's one equation in one unknown. A term that we use for x is variable, because it could stand for any real number. Conceivably, we've figured out that it's actually equal to 2, but it could have been anything in that set of real numbers. All right, so let's talk for a second about one equation in two unknowns. So let's take 3x plus 2y is equal to 12. So here I'm not going to be able to solve for just one number. What I'm going to be solving for is a relationship between x and y. So in particular, I want to figure out what, let me manipulate this so that we have y by itself on one side. So I'll subtract 3x from each side, divide each side by 2. And now I have this relationship. You can see for any value of x what y must be. We can think about that graphically. Now I'm going back to the Cartesian plane. And this is the equation for a line with vertical intercept 6 and slope -3/2. All right, so that's graphically the relationship that we solve for. All right, that's not too amazing, but it's just the first step. Now let's think about two equations and two unknowns. So we'll keep our equation from before. And now our next equation will be minus x plus 4y is equal to 10. Okay, so now we have, if we solve this, we're going to get two relationships. We already did that for the first equation. If we do it for the second equation, I would add x to each side, divide both sides by 4. And that's going to be 2.5 or 5/2. That is again, graphically, it's the equation of a formula for a line. And now it's going to have vertical intercept of 5/2 and a slope of 1/4. If we combine this with our first relationship that we already solved for, it's not a good line, but let's try this again. Where those two relationships both hold, that gives us the solution to this system of equations, these two equations. And that's going to be at this intersection. And so graphically we can see what the solution is, but how do we actually solve it and get numbers? Well, for that I would go back to the scales, but now we have two scales. So there's one scale for the first equation. On one side there's 3x plus 2y, on the other side there's 12. The other equation, minus x plus 4y and 10. Okay, so so now again we're going to just, it's a mystery now, but just a little more involved, a little more intricate. We're going to still just do the same thing to each side of the equation, but somehow we have to end up with at the bottom, we want x on one side of a scale and a number on the other, and y on one side of the other scale and a number on the other side. All right, so how would we do this? This system of equations is really simple, and kind of set it up. It's easy to solve for by substitution. Let's take the second equation, or the second scale, and I'm going to, let's multiply both sides by -1. So that becomes x minus 4y equals minus 10. So over here, that's what we've done to the scale. Now we're going to add 4y to each side. We get x by itself on one side is equal to 4y minus 10. Notice that we're not done. We haven't solved for x because I mean, x is by itself on one side of the scale, but on the other side, it's not just a number, it's an expression that involves y, and we don't know what y is. So what we're going to do then is we're going to take this expression for x, and we're going to substitute it into our first equation. So the first equation is 3 times x, but we've just shown that x is the same thing as 4y minus 10. So we can write that in instead. And according to the first equation, 3x plus 2y is equal to 12. Okay. So, so over here, well, let's simplify that. Well, now let's go ahead and rewrite our scale, just going one step at a time. So now on the left-hand side, there's 3 times 4y minus 10 plus 2y, and that equals 12. All right, now we can simplify. We'll distribute the 3, so we get 12y minus 30 plus 2y is equal to 12. All right, so if we add the two y's, that's 14y minus 30 is equal to 12. Here we're not really doing anything, I'm just simplifying 14y minus 30 on one side and 12 on the other. All right, so now we'll add 30 to each side, and that becomes 14y is equal to 42. So now on our scale, we have 14y on one side, 42 on the other. Now we're going to divide each side by 14, and we get y is equal to 3. So now we have solved for y. To go back and get x, we well, we have this expression for x, which I've highlighted up there. Since we've solved for y, we know that y is equal to 3. That means that x is equal to 12 minus 10, or just equal to 2. So that's 4 times 3 minus 10, and then just simplifying, we get x on one side and 2 on the other. Okay, so that's how you can think about two equations and two unknowns. It's just two scales. We're doing the same thing to each side of the scale. And we now have our solution. I should point out, this is something that you never want to stop doing, but once you've solved for something, just go back and check to see if it works. That is, if x is equal to 2, plug that in here. Y is equal to 3, plug that in. And then when you do that, what do you get? 3 times 2, 6, plus 2 times 3, that's 6 plus 6, and that does indeed equal 12. And then in the second equation, negative 2 plus 12 is equal to 10, so that's good, everything checks out. Okay, so that's two equations in two unknowns. So at this point, that's, kind of all you really need, I suppose. But, just keep in mind, we can be more general about these things as well. So, you can have a system of 3 equations and 3 unknowns. Let's call the third unknown z. Oopsie. Okay, there's just an example. Three equations and three unknowns. You could solve this by substitution the way we did. The idea of the scales still works. It's just now there's three scales. Fortunately, I mean, that would be really messy to solve by substitution. Fortunately, there's really nice area of mathematics called linear algebra, where we figured out how to solve for these things very efficiently, and you don't have to just do it by brute force substitution. But I just want to say you could go even further than this. You could have, instead of three equations and three unknowns, you can have any number of equations in any number of unknowns. Let's stick with the same number though. And now I can't really use x, y, and z because I don't know how many equations there are, but I can use subscripts again. So let's say the first variable is x1. The next variable is x2 and x3 and so on. Last one is xn. There's going to be n equations like this. Oops. Of course, what's missing here is I don't have the coefficients in there. So it might be 3 or -7 or whatever. In general, you can have you can imagine any coefficients in there. And so what I would do is I would just have some notation to stand for coefficients. So for example, in this first one, I have a with a double subscript. There's a 1 and a 1. That's not an 11. Okay. What that means is that this is the coefficient in the first row and first column. Here, I have a with the subscript 1, 2. That is the coefficient in the first row and second column. Okay, so in general, if you have these double subscripts, the first one refers to the row and the second one refers to the column, just a convention that we use. And so you'll see I have n of these coefficients in the first row. And then I'm going to have n coefficients in the second row, but now, the first one will be A21 because it's second row, first column, and then A22, A23, and so on. And then, of course, we add these all up. And it's, harder to write out, but that's what the left-hand sides of the equations look like. On the right-hand side, well, same thing. The right-hand side of the first equation could be anything. Let's call it B1. 1 because it's the first equation. The right-hand side of the second equation is B2, and so on. The right-hand side of the nth equation is Bn. So this is kind of a general system of n equations in n unknowns. The theory extends to these. You could also think about systems of equations where there's more variables than there are equations, or the reverse. The theory is extremely general, and this is just a little taste of it. Okay, so that's it for this installment. I'll see you in the next one.